Hi, everyone. My name is Pranav Atraya. I'm an undergraduate at the University of Texas at Austin. Welcome to my presentation on my paper, High-Speed Accurate Robot Control Using Learned Forward Kinodynamics and Nonlinear Least Squares Optimization. I'll begin with an introduction into the problem this work tackles and motivate our proposed solution. This work tackles the problem of high-speed ground robot control. One example formulation of this problem, shown on the left, involves traversing a desired path at a certain speed or as fast as possible. This desired path can either be specified by a human or by a planning algorithm. Another common formulation is optimal connectivity, shown on the right. Here, the robot is tasked with reaching a goal in as little time as possible, and in doing so, it's free to choose the path. High-speed control is difficult because robots tend to deviate significantly in execution from their commanded controls. Existing work to tackling this problem falls under a few broad categories. End-to-end learning approaches, such as those that apply purely imitation learning or reinforcement learning, have proven to work well in the environments they were trained on, but suffer from a significant data appetite, poor generalizability to unseen scenarios, and most importantly, a lack of safety assurances on the robot's behavior. In light of this, hybrid approaches have been developed. Example works like Wignes et al. Use a classical planner for motion control augmented with a learned cost function. This line of work, however, has not yet been tested in the high-speed driving scenario. Finally, model-based approaches like MPPI employ thousands of parallelized rollouts of a simple forward model and fuse roll information to decode the next action. A significant limitation of MPPI, however, is that it requires an onboard GPU. Our approach, which we call Optim-FKD, falls under both the hybrid and model-based approaches. There are two key parts to our approach: learning a capable forward kinodynamic model and running a nonlinear least squares optimization to compute controls. Key to our approach is our ability to frame many control tasks as a minimization of a least squares objective. In turn, Optim-FKD can be applied to any problem that is specifiable by such an objective. First, we require a learned forward kinodynamic model pi. In this equation, u1 through un are a series of controls commanded to the robot to be executed in sequence. Pi takes as input the current state of the robot and the next commanded control. Using the forward model, we can predict the maximum likelihood observed state sequence x1 through xn hat in a recursive fashion. With this building block, we proceed to formulate the two most common control tasks as nonlinear least squares objective functions. The first is path following. Here we take the predicted maximum likelihood state sequence x1 through xn hat from the forward model and minimize the squared error between it and the desired state sequence x1 through xn star. This yields a control sequence u1 through un star that is optimal with respect to the horizon of the optimization. For the second objective, optimal connectivity, the goal is not only to reach the goal, but to do so in as little time as possible. Hence, there are two parts to the objective function: the term on the left for minimizing final distance to the goal, and a scale term on the right for minimizing time. Note that in addition to the optimal control sequence u1 through un star, n itself is also a variable being optimized over in this case. Ultimately, the crux of our approach is that in a model predictive control fashion, a nonlinear least squares optimization is run continuously at every time step on the robot. In each iteration of the optimization, we begin with the control sequence u1 through un. Each control in this control sequence is fed recursively to the learned forward kinodynamic model pi. This yields a series of maximum likelihood state estimates. This diagram here shows the first two state estimates and the manner in which they were computed. Next, the objective of the control function, along with the Jacobian of the residuals with respect to the controls, is computed. For this example here, the cost measures the deviation between the desired and predicted trajectories. Computing the Jacobian is critical for the application of efficient quadratically converging algorithms like Levenberg-Marquardt. Computing the Jacobian requires gradients to be propagated through recursive model evaluations. Finally, an update is made to the control parameters, and this process repeats until convergence. We test our system on a scale of 1/10 autonomous car shown here. The car is equipped with a Jetson for compute and an Intel RealSense for camera for state estimation. The baseline which we use to compare Optim-FKD against is an inverse kinodynamic, or IKD model. Zhao et al. In a prior work demonstrated the success of using an IKD model for high-speed control. The key difference is that the IKD model computes controls in a single forward pass, not employing any optimization. As will be discussed soon, this approach limits the types of control problems IKD can be applied to. For the first control problem, following a desired trajectory, we plot the Hausdorff distance metric, which evaluates how closely an executed trajectory matches the desired trajectory. Here, lower is better. We can see that for the two types of paths, a rectangle and a figure 8 path, Optim-FKD maintains strictly under 0.2 meter Hausdorff distance, whereas the IKD model is strictly above 0.2 meter distance. We vary the speeds of the robot from 1 meter to 3 meters per second, and even at this high speed, Optim-FKD is able to maintain path following precision. These figures provide a visual grounding for these results. In figures A and C, which depict Optim-FKD execution traces, the desired path in black is followed much more closely than the IKD model in B and D. Next, we show the results for the second control problem considered, optimal connectivity. Recall that the objective here is to reach from the start state in green to the goal state in red in as little time as possible. In doing so, the robot is free to choose whichever trajectory it gets to the goal fastest. Here, the robot is constrained to begin at an angle pi over 2 and end with an angle 3 pi over 2. Our baseline approach, the IKD model, it turns out cannot even be applied to this control problem. It requires a human supply trajectory to follow, dubbed a racing line. This human trajectory is shown in yellow, and the IKD model's execution trace is shown in green. Because the supplied reference trajectory is likely to be suboptimal, the IKD model's performance on this control task is upper bounded. In contrast, we demonstrate that the Optim-FKD approach is general and can be applied without a reference racing line. Optim-FKD follows the blue path, which takes a wider turn, allowing it to reach speeds upwards of 3 meters per second. This, it turns out, is a far more optimal path, as it reaches the goal in 3.3 seconds, whereas the IKD model takes 6.3 seconds to complete. Here are a couple of videos of our experimentation. On the left is Optim-FKD solving the path following task at speeds from 1.5 to 3 meters per second. On the right is Optim-FKD and the baseline IKD on the optimal connectivity task. Optim-FKD reaches the goal in about half the time as IKD. To summarize, our approach presents two main advantages over the existing state-of-the-art in high-speed control. The first is that with its least squares-based formulation, Optim-FKD can be applied to any control task specifiable by an objective function, making it very general. The second is that we are the first to employ a heavyweight forward dynamics model within a real-time MPC framework for high-speed control. The use of a well-learned dynamics model permits useful parameter updates in optimization, yielding better performance. I'd like to thank all the co-authors in this work, and I'd be happy to take any questions.